finish up the conversation on rotational motion, we have to talk about rotational kinetic energy. Last week, we talked about energy and work, and it makes sense that there would also be concepts in the rotational field as well. And so we're going to move on and talk about rotational work and its relationship to tau and the rotational kinetic energy, tau being the symbol for torque. So let's say we have a disk here and we exert a force, a net force, that is perpendicular, and it's kept perpendicular to the radius throughout its action, and it causes the disk to rotate. The net work would thus be that F net times delta S representing the angular displacement in terms of distance as opposed to an angle in terms of meters instead of degrees radians. The net work thus goes into and makes up what we call rotational kinetic energy. So the net work is equal to the net force times the change in distance, delta S, and we can introduce this concept because this is how we find theta, and if we put this here, we can put this here to cancel it out, and so we can represent the same net work in terms of R times F net, and this will be theta. R times F net is equal to torque. So work net is equal to torque net times theta. And this is one of the two equations that we will be using to work problems in this area. The second thing is that we can say that the torque is equal to the moment of inertia times alpha, or the rotational motion, so that work net, if we again substitute here, work net is thus equal to I alpha times theta. And alpha theta, from a previous equation that we had in the translational equations, where omega squared is equal to omega naught squared plus 2a theta, if you rearrange that equation, you get this, and you can substitute this in here, and then you end up with work net is equal to I omega squared times a half final omega minus I omega squared naught. So this looks very much like our translational kinetic energy equation that we used before in the work net equation. So that is also an equation we want to keep it on hand to work some problems. Now, this is called a flywheel right here, and you should think about flywheels in terms of them being the mechanical equivalent of a battery. In other words, a flywheel can store mechanical energy in the form of rotational kinetic energy. This can keep turning in the form of rotational kinetic energy even when the bus stops. And so what it says is you can have these vehicles with these large flywheels. When it goes downhill or while it's moving, you can translate the gravitational potential energy into the rotational energy, and also its translational kinetic energy into rotation. When this bus stops, you don't lose all that energy. It's being stored in this mechanical storage. Thus, it can then be used to accentuate the energy when the bus begins to move again. Now, where it's lost is friction here, and also you have to carry the extra weight of this flywheel. And so just like an electrical battery stores electrical energy, this can actually store kinetic rotational energy. That's how a flywheel works. So let's take a look at a problem here with a flywheel. A large grindstone or flywheel, pictured above, has a radius of 0.32 meters. It is spun exerting a force of 200 newtons and through a rotation of 1 rad, so approximately 57 degrees, perpendicular to the radius. So the force remains perpendicular all the way around. How much work is done? If the stone has a mass of 85 kilograms, what's the final angular velocity? And what is the final rotational kinetic energy? Now let's take a look at how to do this problem. First of all, we have to write down what we know. And we know that the grindstone has a radius of 0.32 meters. And it has applied to it a force of 200 newtons over an angular distance of 1 rad. And we also know that the stone has a mass of 85 kilograms. So work net is equal to tau times theta. We had that in the previous slide. That's going to equal Fr times theta. And F is 200. R is 0.32 and theta is 1. So the total here is 64 joules. And that's the total work that's applied here. So it then asks, if the stone has a mass of 85 kilograms, what is the final angular velocity? Well, work is equal to 1/2 I omega squared, work net. And we assume that there was no initial velocity, so we don't have to worry about that. Now I, if you go back to that table that I showed you before, with a disk, it's going to be mr squared over 2. In this case, 85 times 0.32 squared over 2. And I, in this case, equals 4.352 kilogram meters squared. And we put that in, and we rearrange this. We've got 2 times work net divided by I, and we take the square root of that, and that's going to give us omega. So if we take this 2 times work net, and we calculated work net was 64, I is 4.352, so omega is going to be 5.42 radians per second. Now you can do the next part one of 2 ways. You can say that kinetic energy rotational is equal to 1/2 pi, or 1/2 I omega squared, which is 1/2 times 4.352 times 5.42 squared, and you'll get 64 joules. Or you can say that the work input has to be equal to the subsequent resulting kinetic energy. Here's another problem, and this looks at a helicopter. We have a helicopter in the picture. It has 4 blades. Each blade has a mass of 50 kilos and a length of 4 meters. The blades are considered, or can be considered, thin rods, and the helicopter has a total mass of 1,000 kilos. So the questions are, if the angular rotation is 300 revolutions per minute, what is the rotational kinetic energy? If the linear velocity is 20 meters per second, what is the translational kinetic energy? How high could the helicopter be lifted if all the rotational kinetic energy were translated into potential energy? Write down what we know. The R is equal to 4 meters. The mass is equal to 50 kilos. We have 4 of them. And the mass of the helicopter, total mass of the helicopter is 1,000 kilos. Now, if you look up thin rods rotated on their edge, the inertia is equal to 1/12 mr squared. We have 4 of them, so we end up with 1/3 mr squared. And that's equal to 1/3 times 50 times 4 squared. And if you do that, you get a moment of inertia of 266.7 kilogram meters squared. 266.7. So the rotational kinetic energy is going to equal 1/2 times 266.7 times omega squared. Now, that's the one thing I didn't write down, and that was 300 revolutions per minute. Again, revolutions per minute is not a very useful, and I translated that into 31.4 radians per second. So if we put that in here, 31.4 radians per second squared, and do the math, we get 1.315 times 10 to the 5th joules of rotational kinetic energy. The linear kinetic energy, or translational kinetic energy, is equal to 1/2 mv squared, where m in this case now is going to be the total mass. So it's going to be 1/2 times 1,000 times 20 squared. And this comes out to be 20,000 joules. Lastly, if all this rotational energy were converted into potential energy, the potential energy formula is mgh is equal to the rotational kinetic energy. So that's, if you solve for h, it's going to put the rotational part 1.315 times 10 to the 5th on the top, and then m and g on the bottom, m being 1,000 and g being 9.8. If you do the math here, you get 13.4 meters. Let's end up with a couple of practice problems. The first practice problem is a solid sphere with a radius of 75 millimeters rolls down without slipping an inclined plane that is 5 meters long. What is the angular velocity of the sphere at the bottom of the plane if it requires 10 seconds to reach the bottom? 5 meters long, 10 seconds. Let's write down what we know. The radius of the sphere is 0.075 meters. The distance that it travels, and it's a linear distance here, is equal to 5 meters, and it does it in 10 seconds. So its linear velocity, average, is going to be 0.5, because it's going to be 5 meters divided by 10 seconds. And we know that its initial is 0, and so the average velocity is the initial plus the final divided by 2. So the final velocity is going to equal the average velocity times 2, 0.5 times 2. So its velocity at the bottom is 1 meter per second. Now, it's asking what its angular velocity is, and that's going to equal the linear velocity divided by the radius, and so that's going to be 1 meter per second divided by 0.075. The second problem says a turbine associated with rotating parts has a total moment of inertia, and they just give it to you, 25 kilogram meters squared. It is accelerated uniformly from rest at a speed of 150 rads per second, in 25 seconds. Find the work done by the net torque and the kinetic energy of the turbine. So we know that I is equal to 25 kilogram meters squared. We know that its omega is 150 at the end. And we know that this happens in 25 seconds. So the first question that is asked is, what is the work done by the net torque? So work net is going to equal the kinetic energy, rotational kinetic energy, which is going to equal 1/2 I omega squared, which is going to equal 1/2 times 25 times 150 squared. So work net is equal to 2.81 times 10 to the 5th joules. And the work net is going to equal the kinetic energy. So work net and kinetic energy are equal.